Hi everyone. Yeah, I started experimenting with software-defined radio a few years back, and here are a couple of receivers I picked up. The first one is the RTL SDR, which is a powerful VHF and microwave receiver for about $50. I also purchased an AirSpy R2, which is about the size of a phone charger. It has the option of being stabilized with an external clock source, which for me is really super useful. The SDR radios are often used with LNA preamplifiers to boost the input signal, and the one I have shown here is a Newelec. When used with the SDR Sharp software, these become super sophisticated receivers with a built-in spectrum analyzer. I have an example shown here of part of the FM radio band, and you can see so many signals teased out along with an FM radio station on the far left. A lot of people are trying this out to detect the 1.4 GHz hydrogen 1 emissions from the Milky Way, so I decided to attempt it as well. Of course, you need a good antenna, so I ended up hand making a 1.9 meter diameter parabolic antenna out of aluminum tape and threaded iron stems. It cost me about $100 in parts and is shown here. So the idea with monitoring the H1 emissions is that you can do a time lapse on the SDR Sharp screen and show how the emissions change with time as space rotates around your direction of observation. I have this shown here with the night sky shown on the left and the antenna direction marked by the blue square. I also show some of the other relevant info, such as the reception frequency and the spectrum output on the right, using 5-minute screen captures over the course of a day. You can see that the H1 emissions appear as a hump near 1420 MHz and grow stronger as the Milky Way passes over the antenna and weaker at other times. Also, the frequency rises and falls over the course of the observation period. So although the H1 emissions varied in strength and sometimes were weak or even disappeared, it was possible to estimate the frequency for almost all of the sweeps across the sky, as I've shown here. I have previously seen a few examples of these sweeps shown online, but no one seems to be addressing the obvious question of why the frequency changes over the course of the day. The Earth is moving relative to the hydrogen gas in the spiral arms at 30 kilometers per second as it orbits the Sun. Since the Earth is also rotating, our antenna first faces in a direction receding from the gas, and thus our reception frequency for the H1 emissions are redshifted. When the antenna rotates to the opposite side of the Earth, the antenna is approaching the gas, so the emissions are blue shifted. If we plot out the change in the hydrogen 1 emission frequency over 24 hours, we find that it forms a sinusoidal rise and fall in frequency, which is shown in blue, and which mostly matches the expected Doppler shift, shown in red, for plus and minus 30 kilometers per second. And that would be expected as our angle of observation sweeps around with respect to space. One unexpected result was that at the low end of the graph, the observed frequency fell much lower than what would be expected, i.e. it looks stretched out. This is best illustrated in the next graph. If I subtract out the Doppler shift expected for Earth's velocity around the Sun, we are left with a residual velocity of around plus or minus 16 kilometers per second. What was causing this? In order to try and figure out what was causing this, I decided to collect hydrogen 1 emission profiles over the course of several months, always with the antenna pointed at about 40 degrees above the southern horizon. I then would subtract out the Doppler caused by the Earth's orbital velocity and then plot the residual daily frequency shift in the local time, as well as in sidereal time. I did this on around 10 days over the course of 5 months. What I discovered was that the pattern of emission became scrambled in local time, but aligned nicely in sidereal time. This could only mean that this was tracking a motion of our solar system with respect to the spiral arms of our galaxy. When I looked at the average velocity, it turned out to be around 17 kilometers per second in the general direction of the constellation Ophiuchus. This seemed a bit peculiar, and I was puzzled for a while, since this was kind of implying a motion of the solar system towards the galactic center, which didn't seem right, or possibly that hydrogen gas is approaching us from that direction, which was something that was being discussed in the scientific literature at the time. It then dawned on me that since my antenna was always pointed at around 40 degrees above the horizon, it was only sweeping across a portion of the sidereal sky, and that it might be better to measure it at, say, 15 degrees or 40 degrees or at zenith, etc., and form a complete picture of the blue shift, red shift velocity map of the sky. So that's what I then proceeded to do. Once that analysis was completed and I removed the Doppler caused by the Earth's orbital motion, I then had a full picture of this velocity profile written across the night sky as shown here. The blue shifted velocities are all in blue and the red shift velocities are all in red. As can be seen from this map, the highest blue shift was actually towards Hercules, very close to the solar apex. The highest red shift was in the opposite direction towards Canis Major and practically on top of the solar antipex. This then solved the mystery. This mysterious hydrogen Doppler shift was actually due to our net motion of the solar system towards the solar apex. The expected velocity in this case was around 13 to 20 kilometers per second, but I was seeing it a little bit higher at perhaps 21 to 34 kilometers per second. I suppose the way to understand it best is like this. The main Doppler shift is due to the 30 kilometer per second orbital velocity of the Earth, shown in red. But in addition to this, the solar system is ascending out of the galactic plane at an angle as it rotates around the galaxy, so its current direction of motion is towards the star Vega. This direction is called the solar apex. So although the Sun has a much higher velocity of 230 kilometers per second around the galaxy, we can't see this in the H1 emissions because we are co-moving with the gas and the spiral arms in this horizontal direction. However, because the solar system is ascending away from the spiral arm, this motion with respect to the hydrogen gas is visible as a Doppler shift, and that appears to be what we are detecting with this residual Doppler shift. So I was really impressed with these little SDR radio receivers. For not very much money, you can end up doing some real radio astronomy. So I was quite happy. Anyway, thanks for watching.